Today we're going to learn about radians, a fundamental unit of angular measurement in mathematics. A radian is defined as the measure of a central angle of a circle that intercepts an arc equal in length to the radius of the circle. Let's visualize this with a diagram. Let me show you exactly what this means. First, let's draw a radius of our circle. Now, if we take this radius and lay it along the circumference of the circle, the angle formed at the center is exactly 1 radian. Now, let's think about how many radians make up a full circle. We know that the circumference of a circle is 2 pi times the radius. Therefore, if we keep laying the radius along the circumference, we'll need 2 pi copies to go all the way around. This means that a full circle measures 2 pi radians. Let's look at some important conversions between degrees and radians. Since a full circle is both 360 degrees and 2 pi radians, we can set up these relationships. Pi radians equals 180 degrees, and 1 radian is approximately 57.3 degrees. To convert between degrees and radians, here are the formulas. To convert from degrees to radians, multiply by pi over 180. And to convert from radians to degrees, multiply by 180 over pi. Understanding radians is crucial in mathematics, especially in calculus and physics, where they often simplify calculations and make formulas more elegant. Let's convert 315 degrees into radians. To convert from degrees to radians, we multiply by the conversion factor pi over 180 degrees. This comes from the fact that a full circle is 360 degrees, which equals 2 pi radians. Let's multiply 315 degrees by pi over 180 degrees. This gives us 315 pi over 180. Now, we can simplify this fraction. The greatest common factor of 315 and 180 is 45. Let's divide both the numerator and denominator by 45. Therefore, 315 pi over 180 simplifies to 7 pi over 4 radians. Let's visualize this angle on our circle. 7 pi over 4 radians is equivalent to 315 degrees, which is this angle here. Therefore, 315 degrees is equal to 7 pi over 4 radians. Welcome. Today we'll solve a problem involving the area of a sector of a circle. Let's find the area of a sector with radius 16 centimeters and an angle of 60 degrees at the center. Let's visualize what a sector looks like. A sector is a portion of a circle bounded by 2 radii and an arc. Here, we have an angle of 60 degrees at the center and a radius of 16 centimeters. The formula for the area of a sector is the angle in degrees divided by 360 degrees, multiplied by pi, r squared. This represents the fraction of the circle's area that the sector takes up. Let's substitute our values. We have 60 degrees divided by 360 degrees times pi times 16 squared. Let's solve this step by step. First, 60 divided by 360 simplifies to 1/6. Next, 16 squared is 256. Now we can combine everything. The area equals 128 pi divided by 3 square centimeters. Using 3.14 for pi, this is approximately 134.04 square centimeters. Therefore, the area of the sector is 128 pi divided by 3 square centimeters. Welcome. Today we'll prove an interesting trigonometric identity. We need to prove that 1 over 1 minus cosine theta plus 1 over 1 plus cosine theta equals 2 times cosecant squared theta. Let's solve this step by step. First, we need to combine these fractions. To do this, we'll multiply each fraction by the conjugate of its denominator to get a common denominator. The common denominator will be 1 minus cosine theta times 1 plus cosine theta. Now, let's combine the terms in the numerator. 1 plus cosine theta plus 1 minus cosine theta equals 2. So our expression simplifies to 2 over quantity 1 minus cosine theta times 1 plus cosine theta. Next, let's look at the denominator. Notice that 1 minus cosine theta times 1 plus cosine theta is a difference of squares. This equals 1 minus cosine squared theta. Now we'll use the Pythagorean identity. Recall that sine squared theta plus cosine squared theta equals 1. Therefore, 1 minus cosine squared theta equals sine squared theta. Finally, recall that cosecant is 1 over sine. Therefore, cosecant squared theta equals 1 over sine squared theta. This means 2 over sine squared theta equals 2 times cosecant squared theta, which is what we wanted to prove. And there we have it. We've proven that 1 over 1 minus cosine theta plus 1 over 1 plus cosine theta equals 2 times cosecant squared theta. This is our final answer. Welcome. Today we'll learn about acute angles. An acute angle is an angle that measures less than 90 degrees. Let's look at some examples of acute angles. Here's a 30-degree angle, here's a 45-degree angle, and here's a 60-degree angle. Notice how all of these angles are smaller than 90 degrees. To better understand acute angles, let's compare them to a right angle. A right angle is exactly 90 degrees. Any angle smaller than this right angle is considered acute. Acute angles are found everywhere in the real world. For example, when you partially open a door, the angle formed is usually acute. The hands of a clock often form acute angles, and the corners of many roof designs are acute angles. Remember, an acute angle is any angle that measures less than 90 degrees. Being able to identify acute angles is an important skill in geometry and many real-world applications. Welcome. Today we'll learn about one of the most fundamental shapes in geometry, the circle. A circle is defined as the set of all points in a plane that are equidistant from a fixed point called the center. Let's visualize this definition. First, we start with a point. This will be our center. Then we pick a distance. This will be our radius. Now, imagine taking a point and moving it around the center while always keeping it exactly this radius distance away. Let's identify the key components of a circle. The radius is any line segment from the center to any point on the circle. The diameter is a line segment that passes through the center and has endpoints on the circle. The diameter is twice the radius. The circumference is the distance around the circle. Here are some important properties of circles. 1. All radii of a circle are equal in length. 2. The diameter is always twice the radius. 3. The ratio of a circle's circumference to its diameter is always pi, approximately 3.14159. And that's our introduction to circles. Remember, a circle is defined by its center point and radius, and all points on the circle are exactly the same distance from the center. Welcome to today's geometry lesson, where we'll learn about circumangles. Let's start with the definition. A circumangle, also known as an inscribed angle, is an angle formed by two chords in a circle that share a common endpoint. Let's create a diagram to better understand this concept. First, we'll draw a circle. Let's mark a point A on the circumference. This will be our common endpoint. Now, we'll mark 2 more points B and C on the circle. Now, let's draw the chords AB and AC. These chords share point A as their common endpoint. The angle BAC formed at point A is our circumangle. The arc BC that lies between the endpoints of the chords is called the intercepted arc. Notice how the circumangle is inscribed in the circle, with its vertex always lying on the circle's circumference. To summarize, a circumangle is formed when 2 chords share an endpoint on the circle's circumference. The angle created at this endpoint is the circumangle, and the arc between the other endpoints is the intercepted arc. Let's learn how to construct the incircle of a triangle. First, we'll start with a triangle ABC. Next, we'll construct the angle bisector at vertex A, then at vertex B, and finally at vertex C. The point where all 3 angle bisectors intersect is called the incentre, which we'll label as I. From the incentre, we draw a perpendicular line to any side of the triangle. This length is the radius of our incircle. Finally, we can draw our incircle. This circle will be tangent to all 3 sides of the triangle. The incircle is the largest circle that can fit inside the triangle while touching all 3 sides. Let's learn how to divide an arc into 2 equal parts using geometric construction. First, let's draw our arc. We'll call the endpoints of our arc points A and B, and we'll mark the center of our circle as point O. Draw radii OA and OB from the center to both endpoints of the arc. Next, we'll construct the angle bisector of angle AOB. The angle bisector intersects our arc at point C. This divides our arc into 2 equal parts, arc AC and arc CB. Since the angle bisector divides angle AOB into two equal angles, angle AOC equals angle COB. Therefore, arc AC equals arc CB. And that's how we divide any arc into two equal parts using geometric construction.